Hi everyone, we're one of the teams from Earl of March Secondary School.
I teamed up with my brother Mikhail, and Mikhail mainly worked on the LRT Tour Challenge, and I mainly worked on the Agility Challenge.
Our initial strategy was to research and solve a navigation accuracy problem. This problem is caused by the black art tape, which is reflective, and uh, the robot has trouble seeing it sometimes. Um, this last year, our solution was to reduce the ambient light and heat in the room, um, and that way of a robot works better. But this year we're allowed to modify the robot, and so we want to explore if modifications to the MBot uh, could make a more versatile solution that works in all light conditions. So here's an example of the impact of the light. So this is an original MBot in a highlight environment. So it's trying to drive around the square, but it misses the line and does not work properly. Um, and now this is the same robot, same program, but in a lower light environment. And it actually drives around the square. So we mainly tested the accuracy of navigation of the robot. So the first change we made following the test is we 3D printed and installed new front wheels. These wheels have lower diameter and bring the line following sensor of the robot closer to the surface, allowing it to be more accurate. Next, we installed bigger rear wheels, but with them and the low diameter front wheel, the line following sensors were dragging on the ground, so we had to revert back to the original front wheels. We also experimented with the old 3D printed Arduino robots, and these robots were made for uh, lines made of electrical tape, which are much thicker, and so the sensors were wider apart. Um, and so we cut these sensor holders and glued them back up front to reduce the distance between the sensors, allowing it to follow a narrow line more precisely. Our two unique features in our program are that um, it is object oriented, which allows us to run the same logic, which is in the LRT detour class, on different robots by just implementing the hardware specific uh, methods in their appropriate classes. And our second unique feature is a virtual map, which gets filled in as the robot is uh, exploring the layout. So here is our MBot with bigger rear wheels. The logic itself has two um, priority directions, forward and right. It tries to keep going in any of these directions, um, and when it hits an obstacle, it tries to pathfind around it and get back to those priority directions. Um, when it goes through an intersection more than once, it marks its previous path as a dead end and avoids it during playback mode. So here, for example, it goes into this big dead end, and once it goes back through this intersection, it marks this whole area as a dead end and does not go there in playback mode. And it completed the layout in 48 seconds. Now in playback mode, turns right away because it knows this is a dead end, but you notice it still goes around the whole loop, and that's because it hasn't discovered any of the shortcuts yet, and it doesn't know if there's obstacles there or not. Now when it gets to this intersection, it's going to turn right away because it knows there's a dead end ahead. And It completes this in 26 seconds. This is our modified or 3D printed Arduino robot. The logic here is the exact same and it'll follow the exact same path. And it completes the layout in 57 to 58 seconds. Um, this is our last year robot with original front and rear wheels, and it completes the layout in 62 seconds. Slower than the ORC 3D printed robot. So overall, our strategy worked pretty well. Alternatively, we could have created a program without classes. However, in this case, it would be bulky and hard to manage. In other words, our program is the best solution that we could create, and our key problem of accuracy of navigation was solved.